thank you very much for the interest. Oh, wow, my voice is loud. I didn't know you know my history, so you did your homework. Thank you very much. Well, first I want to say that actually Arizona is a wonderful place to live. It is if you're going to move from Switzerland, you should go to a different planet. Otherwise, you'll kind of feel bad. So that was one motivation for going there. I just wanted to not be any place like Switzerland, and Arizona has its own beautiful elements. So I'm quite happy to be there. On the other hand, I am used to much warmer weather. So I was a little bit surprised yesterday, and I have to thank you guys for a lot of my hosts that came out of the cold and gave me lab tours yesterday, and I really appreciate it. It's been a fun visit so far. Okay, so I'd like to talk a little bit today about high-Q nanomechanical resonators for a variety of experiments in both quantum science and precision measurement, in particular in the field of cavity optomechanics or quantum optomechanics, where I've been working for the better part of a decade now. If you don't mind, I'm going to take off my mask. It's kind of thick. So this is work being done with a number of people. In particular, I want to point out, I'm probably here, honestly, because I'm a colleague of Felipe Guzman's. I have a joint project with him, which started some time ago, which is starting to speed up. And we were good friends when we met at University of Arizona 4 years ago. It's a shame that he moved here, but at least I got to give a colloquium. I've also been collaborating a little bit, and I'll talk about this near the end of the talk, with a couple folks at NIST Gaithersburg. And I also want to highlight that a lot of the work I'm going to talk about today got its origin at EPFL. I'm going to focus actually a bit on that work because for this talk, I'd actually like to focus on nanomechanics, which is, I think, maybe something a lot of you haven't thought about before. So nanomechanics, in particular, ultra high Q nanomechanics, is arguably a solution looking for a problem. In that spirit, I'd actually like to begin this talk by not really posing a problem, but talking about a device that we built a while ago. Talk a little bit about its characteristics, and hopefully out of that will emerge some sort of idea about what these things might be useful for. So I want to talk about this structure behind the title slide here. What you're looking at is the preform for a silicon nitride nanobeam resonator, built over 3 years or so by a young man named Amir Ghadimi back in 2015 to 2018 in Tobias Kittenberg's group. And in 2018, we were starting this device. It turned out to be the highest Q mechanical oscillator ever built for any frequency, any size. And that was a little bit surprising to us at the time. So what does this thing look like? Here are a couple pictures. In red here, you see false colored a thin film of silicon nitride that's been released from a substrate, in blue and green here of silicon. What you can see from the picture here is the dimensions are rather small in absolute units. It's around a few microns wide. Just trying to get used to this pointer. A few microns wide. The unit cells here, it's corrugated in a funny way, and I'll explain why in a second. These corrugations are maybe 10 microns long. What you can't see is how thick this device is. It's only around 25 nanometers thick. So this is a very thin mechanical object. It's a thin film of silicon nitride glass. Another thing you can't see really is the length of this object. So this is a stitching of several images in an optical microscope. This particular device is around 3 millimeters long. We made significantly longer devices than this. But if you calculate the aspect ratio of this beam, it's around 10 to the 5. And actually, back in 2018, that was the highest aspect ratio mechanical device ever made. It's on the order of the other competing devices, which are sort of graphene sheets. And to sort of get a sense of scale here, this would be akin to building the Golden Gate Bridge from Los Angeles to New York. Something which is really extreme at the macro scale, but quite possible actually using modern nanofabrication techniques. So another thing that you can't tell from this picture is that this device is under really high tensile stress. And the reason for that is this silicon nitride is sort of deposited on silicon using a deposition process that occurs at 800 C. And when it cools down, the thermal mismatch between those two materials gives rise to a really large tensile stress, around 1 gigapascal. This is near the yield strength actually of most glassy materials. It's near the yield strength of silicon nitride. To get a sense of scale for that, if you took an optical fiber, 100 micron diameter optical fiber, and suspended a bowling ball from it, you would get this type of stress. And this situation actually naturally arises in, for example, suspension springs for gravitational wave test masses. The reason they do that is if you're trying to make a really high performance vibration isolation system, you start to worry about the violin modes of the suspension springs. And LIGO really wanted to load their suspensions to near the yield stress to push the violin mode frequencies outside of their detection band. This also actually gives rise to an effect called dissipation dilution, which makes the Q factor of those vibrational modes really high. And it's that actually effect that we're leveraging to get these really high Q nanomechanical resonators. I'll talk a lot about that in the middle of this talk. So we were interested in the time of studying the vibration of the violin modes, essentially, of this little nanomechanical beam. This is a picture of one such violin mode. It looks a little bit different than what you would normally associate with the mode of a string or a violin. You can see this sort of localized in the middle of the beam. And the reason for this is that these corrugations here are basically modulating the transverse stiffness of this beam. This is a 1D phononic crystal. And in the middle of this beam is a little defect in which the vibrational modes are localized due to this phononic crystal pattern. So we can think of the transverse vibrations of this beam as a simple harmonic oscillator. It's actually a fairly good model. We could just think of it as described by the equation of motion for a damped harmonic oscillator. But because of the dimensions of this device and the high material stress, the actual mass, damping rate, and frequency of this oscillator are a little bit peculiar. So this is really only sort of 100 microns long and 10 nanometers thick. So the effective mass of this little vibrational mode is around a picogram, which is like the mass of E. coli bacterium. The frequency is around a megahertz. It's pretty high because of the high stiffness of the material and the small dimensions. This sort of by coincidence and also a little bit on purpose is in a technologically interesting frequency. This is a cute little picture of a day traders software. Day traders might update their predictions of the stock market at around a microsecond. It's just to show that if you can do stuff at a microsecond, you can get rich, right? The really peculiar property of this device, however, is its damping rate. So this oscillator is really well decoupled from the environment. And you can think of that, you can characterize that as the ratio of the frequency of vibration to the energy damping rate, something we call the quality factor. For this device, it's around 10 to the 9. So this is the first mechanical resonator ever at room temperature with a quality factor of 1 billion. So if you think of, to get a sense of scale, you can think of scaling this thing up to the size of a guitar string. If you pluck that guitar string, it would vibrate at a kilohertz for a month if it had a Q factor of 10 to the 9. But because this is a 1 megahertz oscillator, it rings down in our lab for maybe 10 minutes. So what can you do with this type of device? Sort of the canonical thing to think about is the sort of utility of a nanomechanical sensor is force sensing. So if I were to push on the top of this cantilever with a localized force, for example, in an atomic force microscope, that would give rise to a displacement. And if I measured that displacement, I could use that to infer the value of the force. And ultimately, the sensitivity of that measurement would be limited by the force equivalent thermal vibrations of this vibrational mode. So that's what I'm showing here. This is the so-called thermal Langevin force, a force equivalent Brownian motion. And it scales as the M over Q factor of the resonator. So for this picogram, Q equals 10 to the 9, 1 megahertz oscillator, the thermal force is something like 1 part in 10 to the minus 18 newtons, so piconewton or attanewton. This is a very weak force. This is somewhat of a romantic force if you're in the mood because we're near Valentine's Day. Just like the gravitational attraction between two human beings separated by 10 meters. Of course, it's a fairly useful force as well. This is roughly the sensitivity of the world's of high performance atomic force microscopes. This is a picture of a magnetic resonance force microscope with an attanewton sensitivity with a 1 kilohertz cantilever. So what you're looking at here is just really a cantilever with a magnet on it that's read out with a laser interferometer. That magnet is used to pick up small magnetic field fluctuations near the surface of a material. And they can resolve with this experiment the spin of single electrons actually by flipping them sinusoidally at the mechanical frequency. It's a kilohertz cantilever, however, that's why they get these high sensitivities operated at 4 Kelvin. So part of the vision for these nanomechanical devices is to do these types of experiments at high speed at room temperature, leveraging high Q. But nowadays, even with these lower Q mechanical oscillators, they can do a lot of interesting things like map out single viruses. This is experiments done in the mid 2010s by people, for example, at IBM in San Jose. Another interesting characteristic of this mechanical resonator, it has a very large 0-point motion. So we can think of a single vibrational mode of this guy as a quantum harmonic oscillator and ask what would the size of the 0-point motion be. It's something we don't often think about for macroscopic mechanical oscillators because it's just not experimentally accessible. Because of the small mass of this oscillator, the 0-point motion is not intractable. It's actually on the order of 10 to the minus 13 meters. It's 3 orders of magnitude smaller than the size of an atom, roughly the size of a large nucleus. That's small, but if you come from a precision interferometry, it's not that small. Actually, it's actually a fairly easy thing to measure with an optical interferometer. You might ask, how does it compare to the sensitivity of the world's most sensitive optical interferometer, gravitational wave detector? This is a long baseline Michelson interferometer that is so sensitive they can resolve the displacement of the end mirrors to 1 part in 10 to the minus 19 meters, which is like measuring the distance to the sun with a hair's breadth. Of course, this is really hard, but it can be done. I'll come back to that. So a little disclaimer about these mechanical devices. The 0-point motion is large, but this is still a very classical mechanical oscillator. And one way of thinking about that is to ask what the ratio is of the thermal energy of one of the mechanical modes here to the energy of a single phonon at a megahertz. It's something like 10 to the 8. So the motion of this mechanical oscillator is dictated by its interaction with the thermal environment. It's not really behaving like a pure state at all. If you wanted to freeze out the thermal motion of this particular vibrational mode, you'd have to cool this oscillator to around a microkelvin, which is colder by a long shot than the coldest solution refrigerator. But it's on the order of what you can get with polarization gradient cooling, for example, of a cesium mott. And there's actually a lot of so there's a lot of thinking about how to laser cool mechanical resonators like this, and I'll come back to that. So the saving grace, if you will, is that even though this has a large thermal occupation, this mechanical oscillator, the time it takes for a single thermal phonon to enter in from the environment, if you will, the so-called thermal decoherence rate, is very small. So the thermal decoherence rate is essentially the time it takes for the energy, for the oscillator to exchange a phonon of energy with its thermal environment. That's given by the thermal energy divided by h bar times the quality factor. For this oscillator, it's around 1 kilohertz. Which is 3 orders of magnitude smaller than mechanical frequency. So effectively, this oscillator is frozen out from the thermal environment for 1,000 cycles. If you were able to prepare in its ground state, it would be a pure state for 1,000 cycles. And this is comparable, for example, to the coherence of the motional state of an ion in an ion quantum computer. This sort of notion of coherency we often think about in terms of the Q frequency product of mechanical resonance. The Q frequency product is larger than KBT or H, and this oscillator should have 1 cycle before it exchanges a phonon with the thermal environment. All right. So what can you do with these types of devices? One sort of application is, if you will, is quantum measurement and control. So if you can use an optical interferometer to resolve the 0-point motion in the thermal decoherence time, and the thermal decoherence time and the oscillator is quantum coherent, then you can use feedback to cool the mechanical resonator to the ground state. So basically, if you can engineer that situation, you can answer the question, is the oscillator in its ground state or not, in the time scale shorter than it decoheres. And with feedback, you can basically stabilize it in its ground state. So this is an experiment we were actually able to do, and I'll talk a little bit more about it in 2015, a long time ago. With a much simpler type of mechanical oscillator operated in a cryostat. It helps for quantum coherence to operate, by the way, at low temperatures. So most quantum optomechanics experiments are done at 4 Kelvin or lower. So another sort of motivation for these types of oscillators is hybrid quantum systems. I won't talk much about this, but suffice it to say that mechanical oscillators can be coupled to many different degrees of freedom. And so you might think of them as buses between different quantum systems. You might be able to couple one to a spin qubit, for example, and to an optical photon, to a microwave photon at the same time, and then use that mechanical intermediary as a connection between these two disparate quantum systems. And it helps in that situation to have a low thermal decoherence rate because you'd like to have the coupling rate between these two systems larger than the thermal decoherence rate. A canonical example in the field of optomechanics where I'm from is take a mechanical oscillator, couple it simultaneously to an optical cavity containing optical photons and a microwave cavity containing microwave photons, and use that to map microwave photons onto optical photons. And there are recipes for how to do that without losing any quantum information, provided the decoherence rate of the mechanical oscillator is low enough. And this might be useful to extract information, say, from a microwave quantum computer onto an optical delay line that operates at room temperature. So our playground traditionally for these types of mechanical resonators is a field called cavity optomechanics, where we take mechanical oscillators and couple them to optical cavities, and then we use radiation pressure forces to manipulate them. And the reason for this, one reason for this is simply it's interesting to see radiation pressure forces. They're typically very weak. It's hard to see them. However, another interesting reason is that you can make very sensitive displacement measurements of mechanical oscillators and optical cavities. And if you can get in the regime actually where radiation pressure force starts to dominate the dynamics of the mechanical oscillator, you can do interesting things like laser cooling. So I want to give you an example of an experiment which really motivated a lot of our research back at EPFL on high key nanomechanics. This is a system that I was showing a sort of a comic picture of in the previous slide of a so-called near-field cavity optomechanical system. So here in red is a silicon nitride beam. Nothing fancy about it, just a beam, no corrugation, not terribly long, 50 nanometers thick or so. And it's placed, and this is hard, in the evanescent near field of a whispering gallery mode resonator. So the blue here is just a piece of glass that's been wrapped in a loop, essentially an optical waveguide wrapped in a loop, and it supports optical modes by total internal reflection around the periphery. And a little bit of the mode leaks out with an evanescent decay length around 100 nanometers, but if you're really good at fab, you can heterogeneously integrate this beam within the evanescent near field. And that allows you to very sensitively measure the displacement of this mechanical oscillator. How do we do that? Well, whenever the mechanical resonator moves, it shifts the cavity resonance frequency because you're changing the local dielectric index of refraction. And you can measure that frequency shift by taking an optical fiber, pumping some light in the cavity, it circulates around, it comes out and gets a phase shift. You can measure that phase shift using standard interferometric techniques. So if we use that technique to make very sensitive measurements of the displacement of this little mechanical resonator, sufficient to resolve its thermal motion with a signal to noise of something like 10 to the 8. So what you're seeing here is the thermal force of being amplified by the mechanical oscillator. And it looks Lorentzian because that's the susceptibility, the shape of the susceptibility of a damped harmonic oscillator. I think it froze. Okay, so this peak here corresponds to the thermal noise. This little twiggle, by the way, on my variables means this is a spectral amplitude. So you can see here that I think the battery might be down. Oh. All right. I'll make this more intimate. So this peak corresponds to the thermal noise. The noise floor here is basically the shot noise of my optical field. And the interesting thing about this experiment is that the noise of the measurement in this essentially cavity enhanced optical interferometer is much, much smaller than what the noise would look like if you had cooled the mechanical resonator to the ground state, this sort of 0 point motion level. So in this regime, we're making a very strong measurement of the mechanical motion. In fact, in principle, with this measurement, we could resolve the 0-point motion in maybe 10 times the thermal decoherence time. And in that regime, actually, the fluctuations of the radiation pressure force due to shot noise, the so-called radiation pressure shot noise, starts to actually overwhelm thermal noise. So if you actually measured the area underneath this peak, you would see something called radiation pressure shot noise manifest as a heating of the mechanical resonator. So we're one of the first people to actually see this type of effect a long time ago with a system like this. You can actually take that measurement and feed it back using radiation pressure or what have you. We just use radiation pressure with a time delay to actually cool the mechanical resonator. This is called cold damping. If you did that, you damp the mechanical oscillator. The area underneath that peak corresponds to the energy of the mechanical oscillator. We can cool it down by many orders of magnitude by this method. And you see actually, eventually the noise floor goes below the shot noise of the measurement. And this is because basically that feedback is introducing correlations between the intensity and phase of the optical field. This is not squeezing, it's called squashing. But it's an interesting regime to be in. Actually, if you did make an out of loop measurement, in this experiment, we're cooled down to around 5 photons. So if you did make an out of loop measurement of the intensity of the optical field in this situation where radiation pressure shot noise starts to overwhelm thermal motion, you would see that the optical field is getting squeezed a little bit. This is because whenever there's an intensity fluctuation in the light field, it gives rise to a displacement fluctuation because of radiation pressure of the mechanical resonator gets written onto the phase. So the mechanical oscillator starts to act like a low noise Kerr medium in this regime where radiation pressure shot noise dominates. And that can give rise to an effect called Ponder mode of squeezing, which was a big, driving impetus for quantum optomechanics back in the early 2010s. So these sorts of effects we really wanted to explore, and a lot of other people in the field were exploring these in the early 2010s to now, actually for the last decade. And it's really given rise to a new playground called quantum optomechanics, where people are trying to basically operate mechanical oscillators and optical cavities in a regime where radiation pressure quantum noise overwhelms the thermodynamics. And ideally also you have a quantum coherent mechanical resonator. And operating in this situation has allowed us to do a lot of interesting things like cool mechanical resonator as ground state, squeeze it, entangle it with the light field, and so on and so forth. I would say that a really big driving impetus for making extremely high Q mechanical resonators, we'd like to do some of these experiments at room temperature. So recently there's been a big push to just make systems that are high Q enough and have a high enough power handling capacity that we can see effects like squeezing at room temperature, cool mechanical resonators to the ground state from room temperature. Just because it's partly because it's sort of a yardstick, and partly because if you really want to pretend like you can make a useful quantum technology, it'd be nice to show that you can do anything quantum at room temperature. And this has really stringent demands on the Q of the mechanical oscillator and its power and the power handling capacity of the cavity optomechanical system. But you notice here that it always helps to have higher Q. All right. And really, what's been driving, I'd say this movement in quantum optomechanics is the ability to make really high Q nanomechanical resonators, all basically based on the same paradigm of thin film strain and thin film glass. So these are a variety of different types of strained thin film resonators, mostly made out of silicon nitride, that have been patterned in fancy ways in order to enhance an effect called dissipation dilution. So I want to talk about that for the middle part of this talk. There's been kind of a paradigm shift, purely from a nanomechanics standpoint, in the last 10 years, but however, driven mostly by curious little experiments in cavity optomechanics. And I want to explore that a little bit. So here you're looking at a plot of the quality factor versus mode volume of many different types of solid state mechanical resonators over the last 20 years or so, compiled by a guy named Matthias and Bowden in 2014. You can see that the Q scales roughly the cubic root of the volume, independent of loss mechanism, independent of geometry of the mechanical oscillator. varying from sort of carbon nanotubes to silicon cantilevers and atomic force microscopes to MEMS oscillators to gravitational wave test messes. And the reason for that roughly is that loss typically gets worse for small objects as the surface to volume ratio increases. So this green region here is a sort of an anomaly. And this is, these correspond to thin film materials under high tensile stress. And it's really been sort of understanding what's going on here that's given rise in the last decade or so to roughly a factor of order of magnitude increase of every 3 years in the quality factor of a nanomechanical resonator using weird techniques, but two in particular. One, just making really large objects, and two, patterning them to make localized modes. So the most recently, people have been able to get really high stress materials, localize them, and achieve quality factors of 10 to the 10 at cryogenic temperatures with crystalline thin film materials. So I want to explore what's actually going on here. I alluded to it in the second slide. It's something called dissipation dilution to the tensile stress. I want to give a slightly, a pedagogical introduction to what that means. Okay, so first, what's going on? There are many types of loss in mechanical resonators. It's actually an interesting subject in and of itself. They come in basically two varieties: intrinsic loss and extrinsic loss. Extrinsic, a classical example, is gas damping, what you typically think of as the source of loss in a mechanical resonator, just coupling this gas molecules bouncing off of it. That can be limited, for example, by operating in ultra-high vacuum. Intrinsic loss might have origins such as, for example, material defects or thermoelastic loss. Now, we often think of two-level system type defects in material giving rise to internal friction. And for these high aspect ratio devices, it turns out that this intrinsic losses dominate. We don't really understand the microscopic origin very well. We just know that we can model the loss mechanism as intrinsic in origin, just acting like an internal friction. So how do we typically model that? We model that with the viscoelasticity, which basically says that the stress and the strain, the stress produced by straining an elastic body is slightly time delayed, which gives rise to essentially a viscous interaction that produces loss. So in continuum mechanics, the way you would model this is by having, say you have some elastic body that's being deformed sinusoidally at some frequency. What the viscoelastic model of loss, of internal loss would look like is that you introduce a complex elastic modulus to represent the fact that the stress produced by this strain, changing the dimensions produces some stress. That stress is out of phase with the strain. So that out of phase of the strain basically introduces a force, is a component of the strain which is out of phase with the component of the stress is out of phase with the strain. So it's basically it's like displacing a mass from the spring, and that gives rise to a restoring force that's proportional to the velocity. And so what that means is that there is power dissipated, and this power dissipated is proportional to the cycle average, the stored energy, and the proportionality is given by this phase shift, this complex argument of the elastic modulus. So the quality factor in general of any sort of elastic body can just be characterized as the stored energy in a vibration divided by the energy loss per cycle, and it's completely encapsulated in this phase retardation, or this complex part of the elastic modulus. So this maps directly onto the so-called Zener model of elastic body as a sort of a mass spring system, as basically a mass suspended from a spring dashpot. And this spring dashpot in complex notation would just be characterized by a complex spring coefficient. What that means is that the energy of vibration of this mass suspended from the spring dashpot system gets dissipated because the restoring force is out of phase with the force, and sorry. Wrong direction. And again, the ratio of the stored energy, the cycle averaged F times force times displacement, and the energy dissipated per cycle, the cycle average force times velocity times a period, is again going to be this characterized completely by this completely by this loss tangent. Okay. So I just want to introduce that notation because if you sort of believe this Zener model on the right, it's very easy to think about how to engineer an effect called dissipation dilution. So in abstract, what I'd like to do is actually superimpose onto this mass spring system a lossless spring. How I do that, it's not clear. But if I could do that, if I could superimpose in parallel onto this mass spring system a lossless spring with no retardation, then I could increase the stored energy without changing the loss. So that's the idea here. I want to take this elastic body, somehow embed it into a conservative force field that increases the energy without increasing the loss. All right. And then in this model, the increase in the Q would be equal to the ratio of the effective stiffness of that conservative potential to the intrinsic stiffness. So you can actually engineer this situation using tensile stress. And one way to think about that is to think of a very simple two-spring, one-mass system. Two springs, mass suspended by two springs between two fixed surfaces. And one thing that we know from basically simple classical mechanics is that if you look at the translational mode of this system, tensily stressing it actually doesn't change the frequency. So if you stretch a string, it actually doesn't change the stiffness of the string if it's a linear string. However, if you have something called a geometric nonlinearity, you can actually engineer a lossless spring by tension. So if I take this two spring system and I actually stretch it with a static tensile force, and you can imagine doing that by, for example, mass loading this spring in a gravitational potential or using some sort of thin film stress, then the restoring force for a transverse displacement of this mass has a term which is due to this tensile stress that's purely conservative. This is called a geometric nonlinearity. And if you believe that this tensile stress has no time delay associated with its response, then that geometric nonlinearity gives rise to this lossless spring effect and dissipation dilution. So a careful continuum model of a string would actually bear out that the magnitude of the ratio of this tensile restoring force and the restoring force just due to internal stresses depends a lot on the aspect ratio of the string. So if I take a string and stretch it, it will undergo dissipation. Its modes will have their quality factors increase, and that increase is given by the ratio of the transverse stiffness of the string due to the applied tension to the transverse stiffness just due to the elastic modulus. The important thing is that actually that the stiffness due to internal stresses has two components. One due to the curvature of the antinodes. So there's work done to actually deform. Basically, when you at the positions where the mode shape has a second derivative that's non-zero, you actually have to change. You have to do a lot of work to change the volume. There's a stiffness due to that, and there's a stiffness due to added curvature of the clamps. This is something we don't often think about sort of as physicists, but real strings actually don't look like sinusoids because at the clamps, the first derivative of the mode shape has to go to zero. So when we model strings and membranes in physics class, we typically think of them as modeled by sine waves, but in actuality, the derivative has to go to 0 at the clamps, and that adds some extra curvature. And that extra curvature gives rise to most of the internal loss in a solid state mechanical resonator. So at the end of the day, you can derive a formula which works pretty well for string and membrane-like mechanical resonators. It says that the quality factor due to this tensile stress gets amplified. And there's two factors here due to the ratio of the stress-induced stiffness to stiffness of the clamp and stiffness of the antinode. The important takeaway is that this dissipation dilution factor depends a great deal on the tensile stress, on the aspect ratio of the device, and it depends also on the ratio of the applied stress to the intrinsic elastic modulus. So you want if you want a high dissipation dilution, you need to have very high aspect ratio, you need to have high stress, and it also would be helpful to get rid of the curvature at the clamps, which motivates looking for techniques to actually so-called soft clamp the mechanical oscillator so it doesn't have that extra curvature. In fact, if you could do that, then you'd go from the dissipation would go as the aspect ratio to the aspect ratio squared. So there's a big win to somehow phononically engineering out the curvature of the clamps, which is something that's eminently doable using lithographic patterning techniques. Are there any situations in which this dissipation dilution naturally arises? Yes, there are. I alluded to one earlier. The suspension springs for test masses and gravitational wave interferometers are basically optical fibers that are maybe half a meter to a meter long. They're 100 microns wide, and they're loaded on purpose with a 10 kilogram test mass in detention near the yield string. So a typical suspension spring in a LIGO vibration isolation system has a tensile stress of gigapascal. The suspensions themselves have aspect ratios of 10 to the 3, and the internal quality factor for most Class A materials is like 10 to the 4. And so the string violin modes of these suspensions are diluted vis-a-vis dissipation dilution to 10 to the 6. Right? It's cute. And in fact, they understood that a long time ago, and they did it on purpose. At the nano domain, you can actually get very similar stresses, but much bigger aspect ratios. The standard way to get high stress, for example, is vis-a-vis thermal mismatch. Silicon nitride on silicon is a very standard thing to do in the silicon industry if you want to strain controllably silicon. Like that's useful, for example, for engineering the electrical transport properties of silicon transistors. So people know very well how to deposit strained materials on top of silicon. So standard LPCVD silicon nitride ends up with 1 gigapascal stress just due to thermal mismatch, for example. This might be, if you work with transmission electron microscopes, it's a standard thing to see a released film of silicon nitride on silicon. It's just a transmission electron microscope slide. These devices intrinsically might have this dissipation dilution. Actually, we realized this purely by serendipity in the field of cavity optic mechanics back in 2009. So I just want to show you a few examples of what you can do by basically etching these silicon nitride membranes or into beams. So a standard silicon nitride, high stress silicon nitride beam has an aspect ratio. I'm sorry that it's not so easy to see here, but standard silicon nitride nano beam, very easy to fabricate in the clean room, can have sort of lengths of 1 meter, thicknesses of 100 nanometers, sitting near the yield strength. Intrinsic Q of most Class C materials is 10 to the 4. It's sort of straightforward to actually get dissipation dilution factors of 10 to the 3. So the very simple beam-like structure can have quality factors of 10 to the 7. It's nice, very easy to fabricate. The strategy which really has led to ultra high Q is to get rid of the motion of the clamps. And the way to do this is very easy. Actually, you just modulate the width of your string. And what this does is it modulates the stiffness that gives rise to a harmonic band gap. And if you embed a defect in this beam that supports a vibrational mode that's in that band gap, then you create a localized mode. And if you're careful, The localization is not too strong, so it doesn't introduce much curvature, but gets rid of the curvature of the clamps. So this is a technique that was invented by a number of people, including a group at EPFL in 2017 and 2018. Get rid of the clamp, and suddenly the dissipation dilution for a regularly sized beam can get quadratically higher. So this 100 micron, you can get 100 micron defects with quality factors of 10^8. So notice what's going on here. You're making objects which are smaller and smaller and smaller, and they're higher and higher in Q. It's kind of a wonderful coincidence. This is very useful for these fun quantum experiments. So it's just some data here. The fun thing is that if you're really careful and you study the vibrational modes of these structures, you get sort of standard dissipation dilution, and suddenly when you hit the band gap and start studying these localized modes can have much higher Q just due to soft clamping. This is not one beam, by the way. This is us measuring 25 different beams and then compiling all the different quality factors. This is a tough measurement. One last thing is that you can also, and this is one of the wonderful things that you can do on the nanoscale, engineer the stress. So if you take a beam and you taper it, what gets conserved is the tension, but in order to conserve the tension, you need to locally increase the stress in proportion to the cross section. So if you choke a beam, you can locally increase its tensile strain. And so you might, this is a cute technique because simultaneously, if you change the pitch of the phononic crystal, you can localize a vibrational mode in a region of high tensile stress. So this co-localization of motion and stress is something which we call elastic strain or strain engineering, which in conjunction with soft clamping is what gave rise to this Q of 10 to the 9 oscillator that I showed in the first slide. So all these fun techniques, you can play at the nanoscale with beams, really simple structure. This is all, by the way, matches just napkin models. It's really nice. It's a compilation of different effects. So I just want to say you can do the same thing with membranes. Membranes are actually a big thing in optomechanics because they have larger surface areas. You can couple them to optical fields. A little harder to model, but they have the same, you can achieve the same effects and get really high quality factors with basically two-dimensional strings as you would one-dimensional strings. Something that's sort of one of the bad things, if you will, about these really small mechanical oscillators is that how do you reflect light off of an object with dimensions smaller than the wavelength of light? It's helpful to have a two-dimensional object so that only one of the dimensions is smaller than the wavelength of light in order to get a strong optomechanical interaction. So actually, although the formalism for understanding this dissipation dilution is much easier for a one-dimensional string, most of the innovation in high-Q nanomechanics has started in membranes and got transferred to strings just because membranes are easier to couple to, say, microwave circuits and optical cavities. Okay, so with that, I want to stop and say I have a group, and I'm doing stuff more recently at in University of Arizona. I just want to go quickly through some of the stuff we're working on. We develop high-Q nanomechanical resonators for fun experiments in optomechanics. We're interested in building, doing room temperature quantum optomechanics and also building sensors out of these devices. And ideally, we want to make a sort of a quantum enhanced optomechanical sensor. So this is a sensor in which radiation pressure, shot noise can be harnessed to either increase your accuracy or sensitivity. So you might think of squeezing the light field in situ and then making a squeezing enhanced force sensor. And another thing we're interested in, and I know I alluded to it in the abstract for those who read it, but I won't talk about it today, is if you can make very weak force measurements, you might be able to look for forces that have never been seen before. And it's been quite in vogue to think about building quantum sensors for searching for dark matter. And mechanical sensors are a natural candidate because the only thing we know about dark matter, if we think it exists at all, is that it interacts mechanically vis-a-vis gravity with mechanical objects. There have been proposals, for example, to basically look for gravitational flybys, if you will, with optomechanical systems. We've latched onto that bandwagon because it's fun. So a few things that we're doing. So our mechanical oscillator, we don't have the fab I'm not a nanofab guy, so I thought, okay, I'm going to start in the lab with something very simple. Our mechanical resonator is a simple silicon nitride trampoline. So this structure actually can have exceptionally high Q, but it's very susceptible to clamping loss. So if you touch the frame, the Q can drop catastrophically. But we have some tricks that we're playing. So we can make these trampoline resonators with Qs on the order of 50 million, as high as 100 million. They have roughly 40 kilohertz oscillation frequencies. Masses are around 10 picogram. They're large enough to interact nicely with an optical field. Force sensitivities of around a piconewton. Interesting thing about these devices is they're big enough and they're high Q enough that actually they also are interesting as acceleration sensors. Acceleration sensor is a sensor for inertial forces. So in this case, you actually want the inertial force is proportional to mass. So you want a larger mass mechanical oscillator. So these devices actually intrinsically have thermal force sensitivities around 100 nanoG at 40 kilohertz, which is not really interesting for many technological applications, but it is interesting for looking for weak inertial forces like dark matter, like might be produced by dark matter. Their 0-point motion here, I'm showing the 0-point spectral density is also quite large, around a picometer, which is eminently accessible without even an optical cavity. And they're quantum coherent at room temperature. So the first thing we did in my lab is characterize these devices. And when we did that, we realized that we could measure them a super high signal to noise without an optical cavity. And so we started doing some very simple experiments where we were asking, oh, can we do simple things like ground state cooling without an optical cavity, just with simple interferometric measurements. And so we were able to cool from room temperature down to around 2 millikelvin or 1,000 phonons, just with a simple Michelson interferometer. So we have a whole bevy of experiments about something called a membrane in the middle optomechanical system. So if you want to get strong radiation pressure interactions, you typically want to recycle the light many times inside of an optical cavity. So you can take one of these trampolines. It turns out that placing a membrane, a thin film, between two mirrors is akin to making it a mirror. So you can make a partially reflective thin film behave like a highly reflective mirror just by placing it somewhere between the node and the antinode of a standing wave inside of an optical cavity. It's something I worked on a long time ago. It's a grad student I've come back to recently. So if we take these trampoline resonators and put them in an optical cavity, then we think we can actually reach the radiation pressure shot noise limiting regime at room temperature with hundreds of nanowatts of optical power, which turns out to be really hard. And the reason for that is for something we didn't really anticipate at all. The thermal motion of these little nanomechanical resonators can be made much, much, much larger than the bandwidth of the line width of the cavity. So we're actually in a regime, something called the thermal intermodulation regime, where the Brownian motion of this little trampoline is much larger than the line width of our optical cavity. And so we actually have to cool our mechanical resonator into the cavity, if you will, in order to even start experiments. So we've been working hard on that. So if Felipe, if anybody knows Felipe Guzman, he's an optimist. And whenever he sees something he likes, he says, let's write a proposal. And so we wrote a proposal together to try to build a so-called quantum enhanced accelerometer based on these trampoline resonators. And the idea there is quite simple. We basically want to functionalize a trampoline-like optomechanical system so that it's moderately sensitive as an accelerometer, and then use radiation pressure to either enhance its sensitivity or its accuracy or its stability. So we want to basically build an accelerometer that we can functionalize with radiation pressure. And in Felipe's much larger accelerometers, the game is, can we see radiation pressure at all? So our system is beautifully simple, actually. We just take two membranes, one a trampoline and one just a membrane, and we sandwich them together on a single chip. So if you have two members of different stiffness, then if you accelerate the chip, they each basically have, because they have different stiffnesses, there'll be a displacement between the two. It's just like pulling. It's just the old tablecloth technique. With this chip, actually, we can make a very simple type of optomechanical accelerometer. And with this accelerometer, by very simple, it's just a simple etalon. It's monolithically stable and beautiful. And the quality factor of the mechanical resonator is above 10 to the 7. So this is a very nice, simple system. We can achieve sensitivities around 100 nanoG. By the way, G is the local gravity at 40 kilohertz, limited by thermal noise over a bandwidth of maybe a kilohertz. And it turns out that this technique of laser cooling is actually useful for measuring incoherent forces, in this case, incoherent inertial forces. And so, and what that means is that actually what you really care about when you're measuring a weak incoherent force is the noise and the noise. And to decrease the noise and the noise, you basically want to average over a larger band, and you can effectively do that by cold damping. And so we can decrease the time it takes to average down this noise to a nominal level using feedback cooling. Doing that, we've achieved sort of 10 nanoG sensitivity at 50 kilohertz. We have a fun collaboration with another professor at the University of Arizona who builds entangled light sources to build a quantum enhanced inertial sensor array. There, the idea is to take this very simple accelerometer and put it in different nodes of an entangled light network, and basically read out the collective displacement of several interferometers with a light field whose different nodes are entangled. And if you do that, then you can make a measurement of the joint displacement with an imprecision below the shot noise level. So it's like making a squeeze light interferometric measurement of a single sensor, but instead of measuring the motion of one test mass, you're measuring the collective motion of several test masses. And this is interesting for inertial sensing because you're usually looking for not local forces, but a distributed force field. But the last thing that I just want to point out is we've sort of gone back to just studying mechanics again. And I'll try not to talk too much on this, but one of the things we were doing in order to make an accelerometer is just try to mass load our trampoline membranes. And every time we tried to do that, the two of the tethers would break. And we ended up with these weird little torsion resonators. And that you see on the right here. They were kind of beautiful, so my student Aman, who fabricates these things, would just take them and put them in the clean hood. And then we started this project with NIST on this quantum enhanced accelerometer array. And one of the guys on the call, who's an old advisor, Felipe's ironically, is a torsion balance expert. He was telling me, "You're an optomechanics guy. Tell me how I can levitate a test mass to make sort of the perfect torsion balance." He's about to retire, so he just wants to do this perfect thing. And I said, "I don't know how to do that," but he said, "Well, if you can't do that, you keep making these high-Q nanomechanical resonators. Can we just suspend the test mass from a nanostring, like you would in a standard torsion balance?" And I said, "Yeah, you can do that, but it's not going to have any. It's not going to help because it's very well known in the field of nanomechanics that this dissipation dilution effect does not work for torsion." He said, "That's not right. There's 100-year-old texts that say that that you do get this dissipation dilution. In fact, it's used all the time in torsion balance community, just like it's used all the time for gravitational suspensions, or gravitational wave detector suspensions." And we went back to the literature, and lo and behold, the guy's right. And he said, "Well, if you want," I said, "Okay, I'll bet you." What we'll do is we'll take this device out of our clean hood, and we'll put it in a vacuum chamber and do a ring down. And it's been sitting there for a year and a half. So we took this device out, the very device that's shown here actually, and we put it in a vacuum chamber. We flicked it. Because of the mass loading, the frequency gone from 100 kilohertz down to around 10 hertz. And the thing ringed down for a weekend. Wonderful. So then we took the mass off and we started studying these devices. So it turns out that there's a whole new sort of twist, if you will, in dissipation dilution, that torsion resonators are also the torsion modes of nanostructures like a beam also experience dissipation dilution. That's not that hard to think about because torsion motion is also transverse vibration, just with a center of mass that doesn't move. But nobody in the field of nanomechanics had realized this, including myself, and I actually rejected papers on the grounds that this effect doesn't occur. So I was quite excited by this. We've been able to sort of realize a whole new class of high-Q nanomechanical resonators based on torsion modes of simple beams, and they're naturally soft clamped. You don't have to do this phononic engineering at all. It's really kind of fun. You get this nice aspect ratio scaling squared for free, but you've replaced the length with the width, and making really wide beams is a little bit harder. So you have higher mass objects. So we're really enamored of these devices. NIST for the torsion balances, me simply for the nanomechanics. We understand the physics very well. It sort of fits our napkin model very well. One of the things that we're interested in doing is actually, instead of doing interferometric measurement, the natural way to make measurements of torsion devices is using deflectometry. So you reflect the beam off the device and you look at the deflection of the optical beam. Purely non-interferometric measurement, but it also has a quantum limit, which has never really been explored because we don't have high-Q nanomechanical resonators. So now we have really high-Q nanomechanical torsion resonators, and we've realized we can make displacements with imprecisions orders of magnitude below the 0 point rotation of these little torsion nanomechanical resonators without any optical interferometry, which is very fun. And so we're thinking about going down the road of doing a new type of sort of torsional quantum optomechanics based on non-interferometric deflection measurements. And also, the real reason we got in this business was to make torsion balances. And these torsion balances themselves are quite interesting. So if you take this device and you turn it upside down, its frequency shifts. Why? Because the mass loading is asymmetric. So actually a good fraction of the restoring force is just gravity. This is the pendulum. And for this particular device, the stiffness due to gravity is half of the stiffness. So the frequency changes by a factor of 2. But the damping rate for this really high Q oscillator is something like 10 microhertz. So we have a 10 hertz shift due to local gravity on top of a 10 microhertz damping rate. So that means that we sort of automatically have a micro G gravimeter on a chip, which is really fun. We're trying to figure out what to do with these devices. But right now we just haven't. Actually, lurking behind all of this, it turns out that if you can make weak inertial forces, you might be able to look for dark matter. And the way to do that is to the caveat there is that these forces are pervasive. They're not local forces. And in order to, you have to somehow suss out whether or not you're seeing some local acceleration or local inertial force versus a dark matter field. And the hitch there is that the predicted force is material dependent. So what you'd have to do is make basically a heterogeneous accelerometer. One of the test masses made of a different material. And that would allow you to sense this basically EP violating force due to dark matter. That's a whole nother talk. But for that, I'd like to stop, say this is a typical outlook in Tucson. These are all the people I've met along the way. Thank you. Yeah. So actually, yeah. So this guy here says his. Oh, repeat the question. Have we worked with 2D materials? If the goal is to embellish on your question, if you're interested in high aspect ratios, why not use 2D materials? I would say, yeah, that's always part of the narrative. It's hard to get strained 2D materials, my understanding. If you stress them, they start to break at the interface, is my understanding. On the other hand, graphene should have a yield strength that's much larger than 10 gigapascal. So in some sense, it's the ultimate material for doing this type of physics. And honestly, I don't know why it still hasn't been achieved yet. Yeah. Yeah. It seems like the natural way to go. Yeah. Yeah. I think it's the right thing to try. Oh, yeah. So they have a lot of, yeah, the internal loss is bad. So I don't actually know what the source of loss is for carbon nanotubes, but the intrinsic quality factor of carbon nanotube, if you don't strain it and you just look at its vibrational modes, they're typically on the order of 1,000. But if that's your starting point, you can try to dilute that by a large factor by applying tensile stress, and maybe it's useful. Yeah. Squashing, yeah. So the squashing here is quite simple. It's pretty easy to understand. Here's see squashing here as well. So here what we're doing is we're making a measurement with the blue light, say, and we're feeding it back onto the intensity of the laser. That a second laser that's being used to actuate the mechanical resonator. So what we're doing is essentially writing the intensity fluctuations of the laser, of one laser onto the intensity fluctuations, measuring, so mapping the phase fluctuations of one laser onto the intensity fluctuations of another. So down at this noise floor, what happens is that basically we are writing the intensity fluctuations of our readout laser onto the position of the mechanical oscillator, and they're correlated so they coherently cancel. So it's purely classical effect, but you get the same effect basically by just basically making a measurement of the intensity of a laser using a photodetector and then feeding it back onto the intensity of the laser. You can squash vis-a-vis that method. It's in some sense squeezed light, but it's not useful in the sense that an independent observer, if you made an out of loop measurement of the motion of the mechanical resonator in this squashed regime, you would see it actually as being heated up. And by the same token, if you're just using intensity feedback to squash a laser field, it would look squeezed from the standpoint of the in loop detector. But if you made an independent measurement, you would see the field is actually has noise being written onto it that produces this correlation that makes it look apparently squeezed on the in loop detector. So it's not distributable. Good question. I have to think about that. I don't have an immediate answer. Optically nonlinear. Yeah, yeah, yeah. Yeah, you might be able to. That's a fun question. So, I mean, you need to have a lot of optical power to get. So it'd be interesting to think of a situation where, first of all, the mechanical current nonlinearity is much stronger. It's much stronger. So to make them comparable, you could think of so if you just had a bare cavity, right? The nonlinear regime would correspond to a cavity frequency shift that's proportional to the injected power. And if you want to do nonlinear stuff, that frequency shift needs to be on the order of the cavity line. But yeah, using nonlinear optics. Yeah. Well, it's not as nonlinear as it gets per se. It is nonlinear in the sense that you have an intensity to phase coupling, right? So optomechanical coupling is occur nonlinearity, but it's not broadband. It's only over the narrow bandwidth of the cavity of the mechanical response, right? And it also has a ton of noise, thermal noise associated with it. Whereas I'm not sure that's the case for optical nonlinearity. in a material. But actually, I don't know how to answer your question. Actually, I think it's a good question. Around 10 meters. Yeah. Is that wrong? What is it? So what is it? So it's even worse. So I could have put them on different sides of the United States. That would have been really romantic. Okay, yeah, but good. I calculated this at the beginning of some talk at the last minute. I've used it for 3 years, so good. I'll correct it. But it's big. It's bigger than 10 to minus 18. Yeah, way bigger. Hmm. That's too bad. Just for comedic purposes.